Welcome to JuliaHub. In this screencast, I'll be demonstrating how to take a published example, edit it interactively on the cloud, and then deploy it using GPU and multi-node deployments on JuliaHub. We'll first start an interactive development environment on the cloud using VS Code. And then we'll make a few changes to a published example in order to gear it for JuliaHub's deployments using GPU compute and multi-node compute. The particular example we'll look at comes from Clima Project's Oceananigans.jl, which is an awesome fluid dynamics library. And the particular problem we're looking at is the ocean dynamics or at the surface level and induced turbulence due to wind and convection. The exact problem here isn't terribly important. The core concepts that we'll demonstrate will apply to many applications across many domains. So let's dive in. JuliaHub.com is where we'll start. You can browse there, and what we want to do is launch an application, the application being VS Code, to get our editor in the cloud. But of course, the first thing we need to do is log in. You can see that this tab is currently grayed out. So let's log in. You can log in with any of the open authentication providers listed, or create an email address, allowing you to log in seamlessly. Once I'm logged in, now you can see I can go to the Applications tab and see the ability to launch a Julia Ide. Before we dig into this pane, though, you can try hitting the Start button, and if you've not added a credit card yet, you'll see an error message there saying, hey, let's add some credit to our account. Clicking OK will bring me over to the Payments tab. Now, you can also get here directly from the hamburger menu in the top right down to Payments. That's where we are. I want to add a credit card. I can do that very simply and easily, ensuring that I have the ability to run code and deploy my applications. Now that my credit card is added, I can go back to that Applications tab, and now I can look a little bit more closely at this launch pane. You can see the ability to dynamically choose the size of the machine that you would like. You can even spin up a machine that has a GPU instance attached to it. Now, these GPU machines are a little bit more expensive, but it's great for debugging GPU problems, especially if you don't have a GPU available to you at home. Today, I don't need that beefy of a machine, so I'll just use the smallest machine available to me. Note 2, you can set up a time limit to make sure that you don't overspend your budget, and hit the Start button. While that's starting, let's dive over to the Packages pane and look at the particular example we'll be examining for our... While that's starting, let's dive over to the Packages pane and look at the particular example that we'll be examining for this demo. We want the package for fluid dynamics. You can just type in what your search key is here, and sure enough, the top package on fluid dynamics is Clima's Oceananigans project. You can go into the documentation, and the example we're interested in is the ocean wind mixing and convection problem. Now, there's a lot of really cool science underpinning this particular example, and I'm not going to go into that. Really, all that I want to demonstrate and what we're going to be showing you is kind of the core infrastructure that this example uses and will make use of in JuliaHub. There's a few things that you do to set up the problem. It's nicely documented in this documentation page of installing the dependencies, setting up the problem state, the initial conditions, all of the sorts of aspects to the problem. There are a few things that we'll key in on, though, as we go through this. The first being that, as it's documented, this model is set up to run on a CPU. Now, Oceananigans is set to work nicely with GPU compute, especially for big problems like this particular one. So that's one place that we'll keep an eye out as we move towards JuliaHub. The other thing that this does is it will run our simulation. And as it's running, it'll output some state information. We'll change this just slightly in our demonstration, and we'll show you why that we changed that. And then lastly, we visualize the problem, which comes out with a really nice animated plot at the end. You can see that by default, this only simulated 40 minutes worth of data. And we'll look at potentially extending that to a longer time period and a more intense computation. So let's go back to JuliaHub and see how our VS Code application is coming along. Once this machine has started up in the cloud, the launch button will have changed to a connect button that I can click. I can also click on this drop-down to look at the currently running instance, manage it, stop or connect to it. I can even launch a secondary instances or examine everything that's going on. All I want to do here is connect. If you've not yet authenticated, this will open up an authentication pane, and you can use the exact same authentication mechanism that you've used to log into JuliaHub itself. That ensures that this is a secure environment for you to use and work with. Now, you can see that we've launched into a default VS Code screen, a welcome screen here. You can create a new file, open folders, do all sorts of things that you would expect with VS Code. There are a few key parts of VS Code that can be helpful as we move forward. One is that on JuliaHub, this data folder is your persistent workspace. This will always be available to all your interactive jobs that you run. So things that you do here will save and will persist. What I want to do is I want to create a new folder to store my work in, and for this particular problem, we'll call it the surface boundary problem boundary, and open up this folder. So now we need to bring in that example file from our documentation. If you'll recall, you have it's nicely documented here using literate programming. We actually want the raw source file. To grab that, we can just go back to JuliaHub, go back, grab into Oceananigans, and go to, instead of the documentation, go to the source code. This will open up the GitHub page for it, and in the examples are what we're after. And here is that ocean, wind, and mixing and convection example. Now I want to move this over into my VS Code instance. There's several ways of doing that. One would be to simply, copy and paste, right? I could copy this and paste it. Rather, what I'm going to do here is I'm going to download it to my computer just to demonstrate how to grab data in general from your computer. So I can download this file to my downloads folder and then go back to VS Code. And in a little bit of a less than discoverable interface for VS Code is we can actually grab any file that we've downloaded, bring it in, and just drag it directly in from my folder into my editor pane here by drag and drop. It'll drop in, and you can see, sure enough, it's done that. Now there's a few things that we need to change. One is I want it to go into my surface boundary, so I'll move it here. We can just, again, click and drag to move it into my surface boundary folder. The other problem is, you'll note it's a .txt, right? When I downloaded from GitHub, we ended up with a .txt. Well, I can just fix that very easily here. Let's start my Julia REPL. And if you're not very familiar with VS Code, kind of the core interface to the editor itself is what's called the command palette. You can find it through the menu system under View, Command Palette. It's kind of obnoxious to navigate to every time. And so there's a very nice and easy keyboard shortcut. On Mac, it's Command-Shift-P. I believe on other systems, it's Control-Shift-P. But it brings up your kind of command line interface to the editor itself. And it's a great interface for working with extensions, like language extensions, like the Julia extension that's already installed. So we can go in here and just type in Julia start REPL. And this will remember your most frequently used commands. And so as you start using them more frequently, they'll appear at the top. So this is, of course, one of my most frequently used commands is to get Julia up and running. Once I've done that, I have a REPL down here. This is, of course, a full-fledged Julia command line interface. I can do all the things that I would expect to, and including, file management sorts of tasks. So using the shell mode, which is the semicolon, I can jump into the shell mode, and I can just simply move my ocean wind and mixing file to the correct location. Of course, first I need to change directories into my surface boundary. When you've launched VS Code, you launch inside that data folder. I want to be working inside my surface boundary. So I'll change directories to this. I could use Julia commands to do it as well, but it's often easier just to use shell commands. And again, I'll use that shell command to move my ocean wind and mixing example to actually have a .jl file. So we now deleted the .txt version, and we can open up our ocean wind and mixing convection.jl. Now, for this project, I really want it to be a reproducible project, and the key interface here is with our package manager. To open up the package manager in Julia, you just hit that close bracket at the command prompt, and it'll open up the package manager. You can see that by default here, I am on my global environment, my default environment for version 1.5. I want to make a specific environment, a local environment, for this project. And I can just simply activate this current folder to allow allow Julia to track this on a per project basis. And now we can follow along with the tutorial. The first line of the tutorial is actually getting our environment set up. Using the package manager, I can run this code just by hitting Control Enter. We'll send these lines of code to my REPL and add in the necessary dependencies for my project. Now, I'll do that once, which will set up what's called the manifest and project for my environment, my local environment here. You can actually go in here and inspect these. You can see that the project is my top level dependencies. And the manifest is all dependencies, and not just their names and their identities, but also their exact versions, their git SHAs, versions, identities, and their dependencies, and so on and so forth. You don't need to know how these files work, but their existence ensures reproducibility as we go through this. So that means that now I no longer need to, in fact, I don't want to dynamically add the packages I need. They're already now a part of my project. They're a part of this folder documented in my project and manifest. And so I can comment this out or even just simply delete the install dependencies section here, because it'll automatically be done every time I use this project. And that's particularly important for deploying into a validated job submission environment, which we'll demonstrate in just a moment, because I want to make sure that the code that's running on my deployed jobs is exactly the same as the code that I'm running locally. So I can go through this and run this locally. I could do this just simply by saying, well, let's include my file, Ocean Wind Mixing Convection example here, hit enter, and that will go through and run this on my interactive environment. And it'll take just a minute to get started, but I'll be back in just a moment once this has completed. So that took a minute or two to complete. You can actually scroll up here, and in the output you can see that it took just over 2 minutes of wall time once the simulation started running. And then after it stopped, it drew some frames of the simulation and saved that out to an animation. And in fact, I can open up that animation right here. It'll open in my VS Code editor environment. You can see exactly the same animation that's in the documentation, which is pretty cool. Now, I want to change this to actually run more efficiently and for a longer time period, right? We're only simulating 40 minutes of real world time here. And we want to potentially extend this out for maybe a day or so. We also want to make use of GPU compute and a bigger machine, right? I intentionally spun up a relatively small, not very powerful and cheap machine to use as my editor environment here, which works just fine for editing, not so great for running code. So let's begin restructuring our code to deploy into a validated test environment. In order to do that, we want to change a few of these things. We've already changed the way that we set up our manifest and project. The next thing that we want to change here is the ability to use CUDA, right? So the CUDA package is how we can use GPU compute. So we can just add in CUDA like this. That will add the GPU package ecosystem to our environment. We then want to add that as one of our usings here, using CUDA. Now, remember that when we looked at the documentation, this was set up to create a model to run on the CPU. We want to change the code here just a little bit to, if CUDA.hasCUDA will run on the GPU instead of the CPU. Otherwise, we use the CPU like that. So this will allow me to dynamically make the most of whatever architecture is available to me. If I have CUDA available to me, well, I'll use GPU compute. If I don't, that's just fine. I'll keep using CPU compute. You can see that this is in fact documented here, but what we've added is the capability of dynamically switching between these two backends, which is nice to enable both dynamic editing on cheaper machines or even on your local machines, and the ability to do so on bigger, beefier, cloud instantiated job submissions. So before submitting this to a GPU job, I want to make a few more changes to the script. First of all, you'll note that as I ran through my iterations here, I printed out a message. And that message was printed out as a simple string print line that gives me a little bit of in detail about what was going on. And this is what happens by default in this published example. And it's a great way of looking at our current progress. I want to change this message just slightly to play a little bit better with Julia's logging infrastructure, and we'll see how this pays off in a little bit down the road. But for now, I'm just going to change this printf macro to an info macro that simply says time step progress, and will simply, instead of interpolating these values from our simulation as parts of our string, what I'm going to do is I'm going to just simply name them in my info statement as keyword arguments. So I is my iteration, time is my model time, delta t here, I can just copy this. Delta t is my pretty time of my wizard, but actually I don't want to use this pretty time function. That's just going to simply, format my time as minutes and seconds. I just want to use the raw values here. So the wizard, so where was I? The delta t, wmax is my wmax, my model, and then my wall time here is this last pretty time, and I just need to make this into a Julia identifier. So put an underscore there and get rid of that pretty time again. So now I've transformed this. I can now delete this formatting expression. I've transformed my progress message from a simple print line to an info message that tags my exact values with a name, and we'll see how this pays off in just a moment. There are a few other things that I want to change here. One here is, well, you see that I ran it for my simulation, ran for a time of 40 minutes. Let's make this a bigger, beefier simulation. Let's go, instead of for 40 minutes, let's do 120 minutes. Then we run our simulation, right? And then bundled into this script was the visualization. Really, I don't need that visualization to be done on a cloud worker. That's going to be something that I will do as I'm examining my model, as I'm examining what the output was. And the way I'll do that is simply by looking at what the simulation output as it's stored out, output. And that's done as a JLD2 file here. That's a great persistence model for Julia sessions. And you can use any output writer you would like here. If you're not using a infrastructure like Oceananigans, it could be as simple as spitting out a CSV file or a zip file of lots of files, or a ping, or whatever you want to have as your output is just fine. But that's going to be what we'll gather from our submitted jobs. And so I don't need to do my visualization on the cloud. Instead, I can do that locally. So what I'm going to do is I'm going to pull out this visualization aspect of my script where I'm creating that GIF, right, of the animated turbulence. Just cut this out and let's create a new file, visualize.jl. And we'll put my visualization of the turbulence here in a secondary file. I want to make sure that this is inside my surface boundary folder. When I created a new file there, it by default was in my data folder. I want it inside my surface boundary folder. So it's bundled up with this project. Okay, so we've made a few changes here. If you'll recall, we've added CUDA as a dependency. We've gone in and dynamically switched our architecture based upon whether CUDA is available. We've changed our progress message to be an info statement instead of a opaque line of text. And we've changed our stop time to be 3 times longer. Now I have just one more thing I want to add to my script here, and that's that I want to tell JuliaHub what file to use as my output. And the way I communicate that to JuliaHub is through an environment variable. I simply set an environment variable that says, hey, my results file to upload. It's a bit of a mouthful, but the idea here is I want to set a file that will upload as our final answer from our simulation. And we'll just grab, what we'll save out, right? We're saving out a file in our current directory, and it's just going to be our ocean wind mixing and convection file. So we'll set this as our results file, and we'll see what that does once we've submitted our job. But now I want to submit this job to my JuliaHub instance with a GPU attached to it instead of my interactive environment. To do that, we'll bring up that command palette again, Command-Shift-P. And this time I want to bring up JuliaHub itself, show an editor pane, a plugin pane that will connect back into JuliaHub. I'll close my file pane here, give myself a little bit more space to see what's happening. You can see that I've authenticated back into JuliaHub. It already knows who I am, and it automatically sees that, hey, I'm working on this ocean wind mixing and convection file. Let's use that as our file to run here. And you can choose whether to submit a non-GPU job with standard CPU cores or a GPU job. And this looks very familiar to the UI that we use to spin up our Julia IDE itself. There's one difference, though, in that this could potentially use multiple nodes. I could potentially spin up many machines. Each node you can think of as an independent machine. Many machines in the cloud to do an even bigger computation. At this point, though, I'm still only using a single machine. That's how I have my simulation structured. So we'll just use one node with a GPU attached, and I have the choice of 2 different GPUs to attach here. One with 12 gigabytes of memory on its GPU, that's a K80 GPU, or one with 16 gigabytes of memory, it's a V100. And just like before, I can limit my time, my cost here. You can see the estimated cost. I know this will take well under an hour, so I can set that just to make sure that I don't overspend my budget, and hit Start Job. Now that'll connect back out to JuliaHub, bundle up all the work that I've been writing on my current directory. It knows that since I'm inside my surface boundary folder here, it knows that it's going to use that environment. Remember those project and manifest files that Julia set up for my local environment. And that's why this portion of my file name is not in italics. That's kind of like the base name of my project. The portion that's in italics is the entry point to my project. So you can see there that my job started. I can scroll down into my previous jobs list here, and you can see here's my surface boundary job that I just submitted. You can also go down and see previous jobs that you've run, including here is the IDE editor that we're currently using. That is itself a JuliaHub job, right? We're running on that, and you can, in fact, even inspect this job and look at it. Once my surface boundary job starts, I'm able to click on my actions and, for example, look at the live logs as they stream in. And I'll bring up a logs viewer that will live kind of peek in on my job, see what's happening, and see the output of my job live as it goes. So first it'll spin up a machine. That can sometimes take a few minutes. Here there is a machine ready for me, so it didn't take any time at all. And it'll download all of the dependencies, all the packages, make sure that all those packages are in the exact same state as I want them to be, as I've been working with interactively and using that project and manifest to do so. So this will take just a moment to download everything. You can see all the outputs here. It's the 100% are all the dependencies that I'm downloading. Give this just a moment and we'll soon be in the main section of our computation. Now we're in the main body of our loop. You can see that we're getting our time step progress messages, and by expanding this, you can see all of the time points here that we're looking at. So now the fun part is, well, we can actually watch these live in a graph. So by scrolling back up, I can pull up a plot here, and let's make this window a little bit bigger. We can watch this happen live. So within each iteration, we can look at what t is here, watch it go for all the available time. The delta t, we can go in and look at the W max, for example, all along as we walk through our simulation. And here's our wall time. So this is a great way of watching our jobs complete. This is actually a live job, but it completed so fast that we didn't even see this happen. This is the beauty of a GPU. In fact, the wall time here, remember it took me just over 2 minutes to do 40 iterations on this small interactive environment. Here, once we finally got up and running into the core section of our algorithm, it took just over 1 minute to do 3 times the amount of work. So you can see this is the nice advantage of restructuring our progress messages, that we're able to plot these things back together. You can do all sorts of fun plots here as time goes on, looking at the delta t time steps over time and such. Let's do I versus delta t. You can see how big of a jump each time step took, and so on and so forth. So this is how we can inspect our jobs as they're running. Well, if they're running slowly enough that they give us a chance to inspect them. But once they're done, well, we can also then go in and remember how we told JuliaHub what results file was going to be there for us. We can go into our actions and download our results. That will save our results file to a temporary file. We can either copy this path, open it, or perhaps most convenient is to save it in a more reasonable location. I'll put it directly into my surface boundary folder here within, and just overwrite my existing JLD2 file and hit OK. Yep, we want to overwrite this. And so now I have my new JLD2 file here. Now I can go back to my visualization here and load back up this file, load back up our visualization. This will take just a bit of finessing to do and to make this happen. But once you have our visualization fixed up to just use our file data, well, then we're going to be able to run this. So again, we can start, bring back up our REPL here. I've already loaded this and already used this, so we can actually set this up, and because we have already run this locally, we can actually just include our visualization file, and that will draw all of our frames for us here. And so now we have more frames because we have more time. It'll take just a little bit to make this slightly more robust. That way you can run this asynchronously or without running your simulation first. But now we have our longer animated GIF, and just as before, we can pull this up and see this go for more than 40 minutes and 3 times longer, and watch the turbulence progress, which is a lot of fun. So that is using JuliaHub to do a bigger computation, just to refresh our memories what we did in order to convert this published example into an example that can run on the JuliaHub and exploit GPU compute. Well, we added CUDA to our environment, and we dynamically switched based upon whether CUDA was available, right? We have our dynamic switch here. We changed our progress message from a simple print line to an info statement that had all of our iterations nicely separated out. And in fact, I missed one pretty time here. We can remove this as well and just keep the raw values, and that allows us to plot those a little bit more nicely and gives us access to all of these to plot. Our simulation output a file, a JLD2 file, that we told JuliaHub was going to be our results file. And so that meant that once we brought up JuliaHub and submitted our job to run, well, then in the results table here, it was able to grab that and tag that as its results that we're always going to now be able to download, tagged to this run of our surface boundary project. We're not only able to see this on VS Code, but we can also go back to JuliaHub and recall that we started our Julia IDE through the Applications tab. There's also this Run Code tab that shows us all the jobs that we've run and allows us to manage them. So you can see here is our surface boundary job. Just like in VS Code, I can pull up those logs. I can see the logs that were printed here and watch the time step progress, see those exact same keywords and such. I can go back to this, and I can also look at details, see exactly what job was created, how it ran, and we also have the ability to add our own outputs to these tables, which I'll demonstrate a little bit later on. And then here's that results link. And when I click on it from the web browser, well, it'll simply download this to my local file, and then I can work on this locally as well if I would like to. So all of these capabilities are available through the web or through your IDE. And that is running code on JuliaHub.